So we're going to talk in chapter 11 about vibrations and waves. We're going to bring back a couple different equations that we've already learned, mixed with a couple new ones. So the big topic in vibrations and waves in chapter 11 is called simple harmonic motion. Okay, and simple harmonic motion, its definition kind of, or regular definition, it's not your book definition of it, but what simple harmonic motion is, it's a phenomena that's characterized by repetitive, identical, or near identical motion. Okay, so anything that's extremely repetitive, extremely identical, extremely steady, any type of motion that's like that, we call simple harmonic motion. And here's some examples of it below. Mass on an extended spring, like you see in the picture right here. A pendulum, which is the most common example of simple harmonic motion, and circular motion, which we've talked about before. There's two main examples that we use. As kind of visual aids for simple harmonic motion. The first of which is a mass on the end of a spring. So here it is right here. This mass that's on this end of this spring right here is at an equilibrium point. Okay, it's at its exact equilibrium because x equals 0. It's being stretched, in which case then it will start to bounce and be compressed, and it will again reach its equilibrium point. That bouncing back and forth motion is what we consider simple harmonic motion. Okay, the object that's in motion, the one that's being bounced back and forth, that's doing this, is called a simple harmonic oscillator. Okay, where have we heard the term oscillator before, or oscillations? Yeah, and a fan, right? Because it spins in a predictable, repetitive motion. All right, we're going to go over quite a few definitions. We're going to talk about quite a few definitions that have to do with this chapter. So the first one is what we call an oscillation or a cycle. Okay, it's a complete back and forth motion. These definitions and these terms are going to be used a lot in this chapter, so it would be good if you had them down. Or if you already know what they are, great. But you need to understand this terminology as we go through the chapter. Okay, so an oscillation, or sometimes your book calls it a cycle, but it's one complete motion of repetitive pattern. So one basically complete back and forth type motion. Okay, so we talk about vibrations, we talk about moving of a spring back and forth, and we also talk about waves. Can you guys visualize what I say when I'm talking about a wave? Okay, that's like a wave that I'm talking about. It's not perfect. I'm not talking about ocean waves. I'm talking about radioactive waves, all the UV rays, all those kinds of things, different types of waves. So an oscillation is basically from the start to the finish. One complete back and forth cycle is what we call an oscillation, or one complete back and forth. All right? Displacement is characterized by an x. Displacement is how far something is measured from the equilibrium point. This is used most often in springs when we're looking at our springs being compressed or stretched. What's displacement measured in? What's our units? Meters. All right, our next one is period, which we've talked about before. Period's a capital T, okay, which means it's a time that it takes this wave or spring or whatever to make one complete oscillation. Okay, it's the time that this object takes, this simple harmonic oscillator takes, to make one complete oscillation. Okay, so time or period is measured in seconds, and it's a capital T. Do we recognize this capital T before? We've used it once before in an equation with frequency. All right. Our next one's a capital A called amplitude. Amplitude is the maximum displacement the spring can reach when we compress or we stretch it. Okay, so the maximum distance that either the spring can stretch or compress, or that the wave will go all the way up or all the way down. And I'll kind of show you an example of that here. Okay, as you look at this wave, here's our equilibrium point right in the middle. Okay, here's where our wave is at equilibrium, is that red point. The amplitude is going to be the maximum that wave goes either up or down. So this distance from the equilibrium point to the top is considered our amplitude, and the distance from our equilibrium to the bottom would be considered our amplitude. Okay, it's whatever distance is the maximum that's from the equilibrium. Do we know what this is called right here along a wave? When it goes all the way up? This is called the crest. Good. And this right here at the bottom is called the trough. Okay, so these are called a crest, and this is called a trough right here on a wave. Frequency we've seen before, it's a little f. Frequency is a little f, not a capital F. This is the number of oscillations that can be completed per second. Okay, and we're introducing a new unit maybe for frequency. I think I mentioned it the last time we used it, but we didn't necessarily label it with this. So the frequency unit is the hertz. So hertz means oscillations per second. All right, wavelength is our next one. Have you seen this Greek letter before? Do you know what it's called? This is lambda. Okay, this is a wavelength. This is the distance between successive identical features in a wave form. So a wavelength is pretty much identical to a complete oscillation of a wave. So if I'm measuring my wave like this, oops. All right, the wavelength basically goes from a crest to a crest, or a trough to a trough, or the equilibrium point to the equilibrium point. Okay, all of those wavelengths should be equal to each other. It's from basically one point on the wave to an identical point on the next oscillation. Okay, so crest to crest, or trough to trough, or equilibrium to equilibrium, wherever you want to go. But it's one complete oscillation is considered the wavelength. We measure that in meters. We still measure that in meters per second. It's still labeled as a V. Nothing really changes there. But we can measure the velocity of our waves, velocity of springs as they move through those oscillations, things like that. Better drawing of the wave itself. So our amplitude, you see, goes from the equilibrium point to its maximum. The amplitude could also go from its equilibrium point to the bottom of the trough. Okay, so it's the maximum that wave goes from the equilibrium point. Wavelength here goes, they measured from crest to crest. Okay, and what's the variable for wavelength? Lambda, the upside down Y. Okay, lambda. And that's measured in meters. I don't know if I said that, but wavelength should be measured in meters. Okay. All right, let's look at some equations we use for simple harmonic motion. This equation should look familiar to you. We've used this before. This is our connection between frequency and period. Frequency is, remember, measured in hertz. It's the number of oscillations or revolutions or cycles or whatever you want to call it per second. So now we can use these bottom equations to connect the wavelength, the period, and the velocity of a certain wave, okay, using this equation. V equals lambda over T. We know that 1 over T is equal to F, so that's how we got this F substituted into the equation down here. So both of these equations do the same thing, serve the same purpose, but we can use either frequency or period depending on which we're given. Equations. Okay. So this is potential energy of the spring only. This is the total energy of the system, kinetic energy plus potential. Remember, this would be energy just for like basically one side. This would be energy before. We know that energy before equals energy after because we're going to assume that all of our systems are frictionless. Okay, so energy will be conserved in all of our problems. Anytime we need to use these equations, we'll know that energy before equals energy after. Okay. Okay. Sorry. Yep. All right, so let's look at this energy as we work through an oscillation of this spring. Okay, here the spring is compressed or stretched? Compressed. And since we see that x is equal to negative a, that means we've reached our maximum compression because we've reached our maximum distance that we can compress that spring. That's what a is. The amplitude is the maximum distance that a spring can be stretched or compressed. Do we understand that part? Okay, so we've reached our maximum here, which means the spring has only potential energy. As it's released and it reaches its equilibrium point, it has only kinetic because it's all in motion. It has no more potential. The spring has absolutely no potential once it reaches its equilibrium point. Okay? As it reaches the other, basically maximum, this is its maximum stretch, it's reached its turning point. It's going to have to start going back this direction. Okay, so it's reached its amplitude or its maximum displacement as far as it being stretched. And then on its way back, kind of halfway between its amplitude and its equilibrium point, it's got both potential and kinetic energy because it's still going to have to go back and compress a little bit to reach its equilibrium point. Okay, does that make sense? So here's some kind of descriptions of that in words if you need to describe it a little bit more. If the spring is stretched or compressed to its maximum, the energy is all potential. I'm not sure why it says mass. It should say spring there. Okay, so this should say if the spring is stretched or compressed to its maximum, the energy is all potential. If the mass is at the equilibrium point, which is right here, the spring has no more potential energy. It's all kinetic. And then when we find it reaching its end points, which is total compression or total stretch, we use this equation, E equals 1/2 kA squared. Okay. The only difference between A and X is that A is the absolute maximum that it can be stretched. X is just the displacement, how far it is away. Okay, so you could always use X if you want to. You just know that A is the amplitude, so that's the absolute maximum that it could go. Okay? So when something has only potential energy, when we're at its maximums, that's why we're using the A, because it's being stretched or compressed to its max. Okay. When we talk about period and frequency of an object that's in simple harmonic motion, believe it or not, the amplitude makes no difference. So the maximum distance you can stretch or compress that object makes no difference in how fast it will complete an oscillation, okay, or how many oscillations it makes per second. It sounds like it should, but it doesn't. It makes no difference at all. So here are the equations that we use to solve for the period and the frequency of an object that's in simple harmonic motion. These are two equations that we'll use pretty often in this chapter. Remember that period will be measured in seconds. Frequency will be measured in hertz, which is just an H, capital H, then a little z. That's what hertz looks like. K is the spring constant, M is the mass. All right, this says an 80 Newton per meter spring is extended vertically from a hook and a 0.6 kilogram mass is placed on the end. Determine the period of the motion. Okay, we're going to see if we can get our answer to match up here. Yeah, spring constant, or K. Mass is equal to 0.60. So if we want to find period, we're using T equals 2 pi times square root of M over K. So we'll solve 0.6 over 80. So T equals what? 0.544, so we match. All right, so what if we're not given the spring constant of a certain of a spring? We have to have a way to solve for that. Okay, if we're not given any of those other variables, also we can use this equation to solve for the spring constant. This is force equals K times X. Okay, and X is our displacement here. If we're talking about a spring that's being held vertically, this force right here would just be equal to the gravitational force. okay, which is mass times gravity. So if we're talking about a vertical spring system here, the force that's acting on it would be a force that's due to gravity. Okay, so M times G. I'm going to show you just kind of a picture of that in a second so we can visualize it a little bit. Okay, so here's our spring that's at equilibrium. This first line would be our equilibrium line. As we attach a mass to it, it stretches a certain distance x. So if we're trying to solve for the spring constant, we would take F over x. And since it's a vertical spring, our force would be our gravitational force, which is mass times gravity. You don't necessarily have to have these equations down. I'm just showing you how we walk through them if it's a vertical spring. This is a family with a mass of 200 kilograms, gets into a 1,200 kilogram car. The springs compress 3 centimeters. What's the spring constant of the car? So there may be a question forming in your head right now. What do you think that is? What's your question? Yeah, which masses do we use? Okay, or do we add them together? The answer to that is when this car is sitting at rest, it's at equilibrium. So those springs were meant and built at equilibrium for that 1,200 kilogram car. So as long as the car is sitting in place, the springs account for that 1,200 kilogram mass. The 200 kilogram mass is what we're concerned with because it's being added on top. Okay, so the 1,200 kilogram car, we don't care about the mass of the car as long as it's at rest. If the car starts bouncing up and down, then we would add the two of them together. Okay. Our x is 3 centimeters, which is 0.03 meters. And we're solving for k. All right, so we know force equals k times x. The force is going to be our gravitational force, which is 200 kilograms times 9.8 equals k times 0.03. Yeah, that's what I had.
Are they usually like, I don't know, can they vary that much?
Divided by m. Does everyone agree? Everyone got that math to come out? Okay. Now let's take this same car, this same spring, and we're going to change the question just a little bit. Okay, so let's say we have the same system, same car, but what's going to be, how far will the springs compress now if the mass increases? So if we have a mass of 300 kilograms that's being set on the car rather than 200 kilograms, what will be the compression? What will be our displacement here? So will our spring constant change at all for the car? No. Spring constant won't change. All right. The mass changes, which will change our gravitational force. So now we'll take 300 times 9.8. That'll be equal to K, which we solved to be 65,333. And we'll solve for X, which will be our displacement, which will be how far that car compresses basically when this new mass is added. No, what'd you get? 0.045 meters. Good, which is just 45 centimeters. Yep, 4.5. Okay. Questions about that one? We don't have to change the centimeters, just because that's what our original started in was 3 centimeters, so just as a comparison, I put it back. This is going to require us to use one of our new equations for frequency. Okay, so this says a fly with a mass of 0.15 grams is caught in a spider's web that vibrates at a frequency of 4 hertz. What's the value of the spring constant of the web? So our mass is 0.15 grams, which in kilograms makes it really small, 0.00015, or you can put it in scientific notation, which is 1.5 times 10 to the negative fourth. You don't have to put it in scientific notation. And our frequency is 4 hertz. All right, so we can't solve for spring constant just using F equals Kx because we don't have any of those values. Okay, we have to use this equation, F equals 1 over 2 pi times square root of K over M. Sorry, you don't really need the parentheses in there. Going to go ahead and plug in our numbers here so we can see it. Okay, doesn't really make a big difference the way we do it, but actually no, I'm going to do variables because it's easier. Okay, so if we want to get K by itself, what's the first thing we need to get rid of?
2 pi.
The 2 pi needs to go first. Okay, 2 pi needs to go first. So to move it to the other side, we're going to multiply or divide by 2 pi. We need to multiply by 2 pi to get it to the other side. So we'll take 2 pi times F equals square root of K over M. Our whole goal here is to get K by itself. All right, so now to get rid of that square root, we need to do what?
Square it.
We need to square both sides. Okay, so that leaves us with 2 pi F squared equals K over M. And then to get M by itself, to get K by itself, we're going to just multiply by M, multiply by M. All right, so now our new equation here says K equals M times 2 pi F, and that whole term is squared. All right, so now we can go ahead and plug in numbers here to solve for K. Do we have a value for K? Good. 0.095 Newton meters. All right, we're going to change our question just a little bit here. We're going to talk about the same web, talk about the same system, but our question's going to change just a tiny bit. Okay, so remember that our spring constant here was 0.095. At what frequency would that same web vibrate if an insect with a 0.5 gram mass were trapped? So the spring constant of this web is not going to change. It's still just as flexible or just as stiff as it was the first time. We have a different mass this time. Okay. So our mass is 0.5 grams, which is 5 times 10 to the negative fourth, or 0.0005. Whatever way you want to write it is fine with me. And from our last problem, we know that K is equal to 0.095. Okay, that doesn't change throughout the problem. So we need to divide this first, then square root it, and then take it times 1 divided by 2 pi. We have to be careful when we plug this into our calculator, and if you need help doing that, please ask. Okay. If we're in frequency here, we got 2.19. Our units should be hertz.